Proof of history, PoH, emerges as a groundbreaking consensus mechanism primarily utilized by the Solana blockchain, representing a paradigm shift in blockchain technology. Distinguished from traditional mechanisms such as proof of work, PoH, and proof of stake, PoS, PoH introduces a revolutionary method of timekeeping within the blockchain. This innovation lies in its unique approach to encoding the passage of time cryptographically, generating a sequence of outputs from a hash function where each output is dependently linked to its predecessor. This sequential timestamping creates a reliable historical record, establishing the exact timing of events or transactions. PoH's efficiency is further enhanced by its high throughput capabilities, enabling the Solana blockchain to process transactions with greater speed and less complexity. By reducing the communication overhead typically associated with achieving consensus in traditional systems, PoH streamlines the verification process. Furthermore, its integration with PoS in Solana leverages the strengths of both mechanisms, fostering a robust and efficient blockchain environment. While PoH has significantly advanced the scalability and efficiency of blockchain technology, it also prompts discussions about centralization and security, reflecting the dynamic and evolving nature of this field. Proof of history, PoH, is a unique consensus mechanism used primarily by the Solana blockchain. It's designed to create a more efficient and scalable blockchain system. Here's how it works. Timekeeping innovation. Traditional blockchain systems like Bitcoin and Ethereum use proof of work, PoH, or proof of stake, PoS, mechanisms, where consensus on the state of the blockchain is achieved through mining or staking, respectively. These processes can be time-consuming and energy-intensive. PoH, on the other hand, introduces a novel way of timekeeping within the blockchain. Sequential timestamping, PoH works by encoding the passage of time in a cryptographic way. It generates a sequence of outputs from a hash function, where each new output depends on the previous one. This creates a historical record that proves that a certain event or transaction occurred at a specific moment in time. High throughput and efficiency. By having a verifiable record of time, PoH allows the Solana blockchain to process transactions more quickly and efficiently. It reduces the need for complex consensus protocols since the order of transactions and the time they occurred are already established. Reducing overhead. In traditional blockchain systems, reaching consensus often involves a lot of communication overhead among nodes. PoH reduces this overhead by providing a way to verify the time and order of events without needing extensive communication. Integration with proof of stake. Solana combines PoH with a proof of stake, PoS, mechanism. PoH is used for creating the historical record of transactions, while PoS is used for the actual consensus on the state of the ledger. This combination aims to leverage the strengths of both mechanisms. Use cases and performance. Solana's use of PoH has allowed it to achieve high transaction speeds and low fees, making it suitable for applications requiring high throughput, like decentralized finance, DeFi, platforms, NFT marketplaces, and other decentralized applications. Security and decentralization trade-offs. While PoH offers efficiency and speed, it also raises questions about centralization and security. Some critics argue that the mechanism could lead to centralization, as the process requires significant computational power, potentially limiting the number of nodes that can effectively participate. Proof of history represents an innovative approach to solving the scalability and efficiency challenges in blockchain technology. However, as with any consensus mechanism, it involves trade-offs and is subject to ongoing scrutiny and development within the blockchain community. The importance of proof of history, PoH, in the blockchain space can be understood through several key aspects. Enhanced scalability. One of the biggest challenges in blockchain technology is scalability. Traditional mechanisms like proof of work, PoH, and proof of stake, PoS, can struggle with high transaction volume, leading to slower processing times and higher fees. PoH addresses this by enabling a blockchain to handle a larger number of transactions efficiently, making it a valuable solution for scalability issues. Improved efficiency. By providing a cryptographic way to keep time, PoH reduces the need for extensive communication and consensus-reaching processes that can be time-consuming and resource-intensive in other blockchain systems. This efficiency is crucial for applications requiring fast and frequent transactions, such as financial applications, gaming, and online marketplaces. Innovation in blockchain technology. PoH represents a significant innovation in blockchain technology. It challenges traditional approaches to consensus and offers a new way to think about how blockchains can operate. This kind of innovation is vital for the evolution and advancement of blockchain technology. Attractiveness for developers and enterprises. The high throughput and efficiency of PoH-based blockchains like Solana make them attractive for developers and enterprises looking to build and deploy decentralized applications, dApps. Faster transaction speeds and lower costs can lead to a better user experience and more feasible business models for blockchain-based applications. Potential for wider blockchain adoption. The limitations of current blockchain technology are often cited as barriers to wider adoption. By addressing these limitations, PoH contributes to making blockchain more accessible and practical for a broader range of applications, potentially accelerating the adoption of this technology in various industries. Encouraging further research and development. The development of PoH stimulates further research and innovation in the blockchain space. It encourages the exploration of other novel consensus mechanisms and solutions to existing challenges, fostering a more dynamic and forward-thinking blockchain community. Discussion on decentralization and security. While PoH improves efficiency and scalability, it also sparks important discussions about decentralization and security in blockchain systems. Understanding its trade-offs helps in developing a more nuanced view of what different consensus mechanisms offer and what their limitations are. In summary, proof of history is important because it represents a significant step forward in addressing some of the fundamental challenges in blockchain technology, particularly around scalability and efficiency. Its development and adoption have implications not just for the technical aspects of blockchain, but also for its practical use cases, adoption, and the ongoing evolution of this rapidly developing field. To understand how proof of history, PoH, works in a blockchain context, let's break it down into its fundamental components and processes. Cryptographic timestamping. At its core, PoH is a sequence of computation that can serve as a cryptographic timestamp. It uses a specific kind of function known as a verifiable delay function, VDF. This function takes a certain amount of time to compute, but the output can be quickly verified by others. Hash function sequence. In PoH, a hash function repeatedly processes a piece of data. Each output of the function is used as the input for the next iteration. This process creates a sequence of hashes, each dependent on the previous one. Creating a historical record, each hash represents a unique moment in time because it's computationally impossible to predict the output of a hash function without actually performing the computation. This sequence of hashes forms a historical record of when each step in the computation was completed. Timestamping transactions. Transactions are mixed into this sequence. Each transaction is hashed along with the current state of the PoH sequence. This action timestamps the transaction, proving that it occurred after the previous hash in the sequence and before the next. Reducing communication overhead. In other consensus mechanisms like PoH or PoS, nodes typically need to communicate extensively to agree on the state of the blockchain. PoH reduces this need because the sequence of hashes provides a reliable timeline of events, reducing the ambiguity about the order and timing of transactions. Integration with proof of stake. In systems like Solana, PoH is used in conjunction with PoS. PoH provides the historical record, while PoS is used to validate the current state of the blockchain. Validators stake their tokens to participate in the consensus process, adding an additional layer of security and decentralization. High throughput and efficiency. Because PoH allows transactions to be timestamped quickly and in an order that's easy to verify, it enables the blockchain to process and confirm transactions rapidly. This leads to high throughput, making PoH-based blockchains suitable for applications that require fast and frequent transactions. Security considerations. While PoH improves efficiency and scalability, it does have unique security considerations. Ensuring that the sequence of hashes cannot be manipulated and that the timestamping process remains tamper-proof are vital for maintaining the integrity of the blockchain. In summary, proof of history works by creating a chronological record of events, like transactions, using a sequence of hashes from a hash function. This method provides a way to prove the time and order of events without the need for extensive communication between nodes, thus enhancing the efficiency and scalability of the blockchain. When combined with mechanisms like proof of stake, it forms a robust system for managing a decentralized ledger. Proof of history, PoH, as a consensus mechanism is primarily associated with the Solana blockchain. The key figure behind the development of proof of history is Anatoly Yakovenko. Here's a brief overview of his role and contribution. Anatoly Yakovenko is the co-founder of Solana and the primary architect behind the proof of history concept. Before founding Solana, he had extensive experience in the technology sector, including a significant tenure at Qualcomm. His background in distributed systems and compression algorithms played a pivotal role in conceptualizing and developing PoH. Solana's development team, while Yakovenko is the leading figure, the development and implementation of PoH and the Solana blockchain involved a team of engineers and developers. This team brought together expertise from various fields, including distributed systems, cryptography, and software engineering, to turn the concept of PoH into a functional blockchain protocol. Community contributions. Like many blockchain projects, Solana's development has also benefited from the broader community of developers, contributors, and enthusiasts in the blockchain space. Open source development, community feedback, and collaborative efforts have played a role in refining and improving the PoH mechanism and the Solana blockchain as a whole. Collaborators and partners. Solana's journey also involved collaborations with various entities in the crypto space, ranging from investors to technology partners. These collaborations have been instrumental in providing the necessary resources, insights, and industry connections crucial for the development and adoption of the PoH-based blockchain. Anatoly Yakovenko's vision and technical expertise, combined with the efforts of the Solana team and the wider blockchain community, have been fundamental in bringing proof of history to life. This collaborative approach is typical of many blockchain projects, where individual leadership blends with community-driven development. Proof of history, PoH, is a novel consensus mechanism primarily used in the Solana blockchain. Developed to address scalability and performance limitations common in traditional consensus mechanisms like proof of work, PoW, and proof of stake, PoS, PoH emerged as a significant innovation in the blockchain ecosystem. The core of PoH lies in its use of a verifiable delay function, VDF, to generate timestamps for each block, ensuring the immutability and authenticity of these timestamps. This method allows for the establishment of a verifiable order of transactions, which is critical for the integrity of the network. It significantly enhances the efficiency and security of blockchain networks, particularly those requiring high transaction throughput and quick finalization. Solana, leveraging PoH, achieves high scalability and low transaction costs, processing transactions in parallel and using slots with their own leaders for validating and ordering transactions. This structure enables Solana to handle a large number of transactions per second, making it suitable for applications like decentralized finance, supply chain management, and gaming. PoH differs from PoH and PoS in several ways. Unlike PoH, which relies on miners solving computational puzzles to validate transactions and create new blocks, PoH is not resource-intensive for transaction processing. It also differs from PoS, where participants stake their tokens as collateral to validate transactions and secure the network. Solana's PoH combines the use of a trusted time source with a Byzantine fault tolerance, BFT, consensus algorithm to achieve consensus, offering high scalability and throughput. However, PoH is not without its challenges. Its dependency on a trusted time source introduces potential security vulnerabilities, such as the risk of the time source being compromised. Maintaining the PoH ledger requires additional computational and storage resources, and as the network scales, ensuring efficient management of the PoH ledger remains an area of research and development. There's also a risk of centralization of power in the consensus mechanism, as validators with a higher stake can potentially control the network's operations. The environmental impact and energy consumption of PoH are also concerns, though it's more energy efficient compared to PoH. Additionally, the computational intensity required for generating and verifying large amounts of data in PoH could potentially limit its scalability and accessibility, particularly for smaller players in the blockchain ecosystem. Recent developments have seen other companies and networks begin to explore the potential of PoH. Arweave, a decentralized storage network, plans to integrate PoH to improve its storage and retrieval processes while maintaining security and data integrity. Future applications of PoH are expected to expand into areas like digital identity, supply chain management, and more efficient DeFi applications. In summary, while PoH is a promising innovation in the blockchain space offering increased security and efficiency, it's crucial to carefully weigh its potential benefits and drawbacks. Ongoing research and development are expected to further refine and enhance the capabilities of this consensus mechanism. Proof of history, PoH, while innovative, does have certain limitations and aspects that warrant careful examination. Centralization concerns, PoH relies on a single source of time to record events, which could lead to centralization. The mechanism requires significant computational power, potentially limiting the number of nodes that can effectively participate, thus reducing decentralization, a key principle of blockchain technology. Security risks. The dependency on a single time source in PoH introduces potential security vulnerabilities. If the source of time is compromised, it could affect the integrity of the entire blockchain. This is in contrast to more distributed consensus mechanisms like PoH and PoS, which don't have a single point of failure. Scalability and performance challenges. While PoH aims to improve scalability and performance, the mechanism itself requires substantial computational and storage resources. As the blockchain grows, efficiently managing the PoH ledger, particularly for smaller nodes, could become increasingly challenging. Energy efficiency and environmental impact. Although PoH is more energy efficient compared to PoH, it still requires significant computational resources, which has environmental implications. The energy consumption and carbon footprint associated with maintaining a PoH-based blockchain need to be considered. Limited adoption and proven use cases. Currently, PoH is primarily used by Solana. Its broader adoption and long-term viability across different types of blockchain applications remain to be seen. Other consensus mechanisms like PoH and PoS have been more widely adopted and tested in various use cases. Complexity and technical barriers. The technical complexity of implementing and understanding PoH can be a barrier for new developers and participants in the blockchain space. This complexity could hinder the wider adoption and understanding of PoH-based systems. Development and refinement needed. As a relatively new technology, PoH continues to require development and refinement. Ongoing research and development are crucial to address its current limitations and to fully harness its potential benefits. In conclusion, while Proof of History offers an innovative approach to addressing blockchain scalability and efficiency, it is important to recognize its limitations, potential risks, and areas where further development is needed. As with any technology, a balanced and critical view is essential for its evolution and adoption. In conclusion, Proof of History, PoH, represents a significant evolution in blockchain consensus mechanisms, distinguishing itself from traditional methods like proof of work, PoH, and proof of stake, PoS. By innovatively encoding the passage of time within the blockchain, PoH establishes a dependable historical record, enhancing transaction processing efficiency and reducing complexity. Its integration with PoS in Solana exemplifies a hybrid approach that leverages the strengths of different mechanisms to create a more robust and efficient blockchain environment. While PoH has undoubtedly advanced blockchain scalability and efficiency, it also brings to the forefront discussions about potential centralization and security challenges. This highlights the dynamic and evolving nature of blockchain technology, where new innovations continually reshape the landscape, balancing the trade-offs between efficiency, security, and decentralization.